My name is Mark Vincent Jason. I am part of the X-Force Research and Development team. So I work for the BPS technology. Basically, BPS is a behavioral antivirus. So what I do, my day-to-day job involves analyzing a bunch of malcodes and then attempt to generate a behavior pattern for it, so that if a new malcode attempts to use this new technique, this specific technique, so they will be detected. So from time to time, my work involves tracing packers. This is for malcode analysis, for posting malcode reports, or for engine support. So I work with developers developing the engine. So I trace the malware and identify what it does, and then tell the engine developers what it does, and then try to support the particular packer. So my talk is about anti-reversing tricks employed by packers. So packers are one of the most interesting things in the interesting puzzles to solve in the reverse engineering field. So some of them are created to protect legitimate applications, but they're also used by malcode. So over time, researchers on the other sides, the one who developed the packers, they develop anti-reverse engineering tricks, while reversers on the other side, like malcode analysts, find ways how to break these protections. So anti-reverse engineering tricks are also interesting to look at, because we gain a lot of knowledge about Windows internals. So this talk focuses on commonly used and interesting anti-reverse engineering techniques employed by packers. It also discusses ways on how to bypass and disable this anti-reversing tricks or techniques. So this is what you use if, for example, automation tools like failed, or you are an antivirus. If you are a researcher helping engine developers to tell them what the packers tries to do. So information presented can also be used in identifying and solving anti-reversing tricks. So my talk is divided into several parts. The first part involves debugger detections. It is how packers attempt to detect the debugger, or if a debugger is running the system. The other one involves identifying breakpoints or patches in the packer stub. And the next one is anti-analysis, and the others and advanced techniques used by packers. And I will also briefly discuss about the tools that can be used. So the first one is debugger detections. So the first technique is the most basic and the most obvious anti-debugger detection technique. So this one just checks the being debugged flag of the PEB. So the PEB can be so FS 30 points to the PEB. So the API is debugger present, check this particular flag. So because this check is very obvious, some packers try to obfuscate it. So this is an example call. So the packers try to call is debugger present. If it's returned a non-zero value, it means the debugger is detected. And the other one particularly directly checks the PEB for the being debugged flag, and then just branch if a debugger is found. So this particular debugger detection technique can be easily bypassed by patching the PEB being debugged flag, or you can use OLE script to patch it automatically by the DBH command, or OLE advanced. It is an OLE DBG plugin that you can use to automatically patch this flag. So the next one is one of the not really documented debugger detection technique. So when you load when a program is loaded by a debugger, when a program is not loaded by a debugger, usually the PEB anti-global flag is set to 0, but it can be overridden by a register entry or T flags. So if the program is loaded by a debugger, usually it will contain 70 as its value. So packers can identify if a debugger, if the program is being debuggered by checking this flag. If it contains a non-zero value, it means that the process is probably being debugged. So other flags that the packer can check is the process heap flags. Basically, because the flags are set in the anti-global flags, the initial heap created for the process heap, is usually 2 if the process is not being debugged. But if the process is being debugged and anti-global flags has a different value, so process heap flags will contain a value different from 2. So usually packers will check the anti-global flag and also check the process heap flags or the process heap force flag. It will check if flags is 0 or force flags is 0. So this is an example how to patch. This is an OliScript a sample how to patch the anti-global flag and the process heap flags and force flags. So it just retrieve the PEB and then patch the anti-global flag with 0, and then retrieve the process heap and then patch the flags and the force flag fields to 2 and 0, like the process is not being debugged. So, by the way, in the CD there will be a white paper there that contains the sample codes. So, another debugger detection technique is via the debug port of the eProcess kernel structure. Basically, if the process is being debugged, the eProcess debug port field will contain if the process is not being debugged, the debug port will contain 0. Otherwise, it will contain a non-zero value. So if you are a packer and if you want to check it using in the native layer, in the NTDL layer, you can query the debug port field using a NT-query information process with the process information class equal to process debug port. And if returned -1 in the return variable, it signifies that the process is probably being debugged. So in the kernel 32 layer, you can use a check remote debugger present. Basically, it just calls the NT-query information process to check if a particular process is being debugged. So one way to solve this is another OliScript sample. What it does is to try to set a breakpoint in NT-query information process and then find the point where it tries to return. And then it will set up a breakpoint handler. So in the breakpoint handler, it will try to check if the process information class being passed is process debug port. If that is the case, it will try to patch the returned process information to 0. So it will try to fake the return value of NT-query information process. So debugger interrupts. So by default, a single step and breakpoint exceptions generated by int1 or int3 is not passed to the exception handler. So if after the int1 int3 instruction, the exception handler is not invoked, it means that the process is being debugged. So flags can be set inside the exception handler to mark that it had been executed. So there are times that packers use debug break instead because it uses int3, it invokes int3 also. So here's an example. So in this example, you will see it's about to invoke int3. So the technique here is that this is a sample code I did. So the technique here is that if the process is being debugged, after I step through the int3 EAX, if the process is not being debugged, after I step through int3, EAX should be changed to -1. But if you just trace it, like you press F7, so it will just say int3 command at debugger, then address, and then EAX is not modified. So it means that you will be detected. So it says that it had detected the debugger through a debugger interrupt. So one way to solve this is to when it displays int3 command to debugger address, you can try to go to the exception handler by a view and then SEH chain. So this one is the exception handler in the top of the chain. So you just double click it and then set a breakpoint in it. And then you will need to pass the exception generated by int3 to the exception handler by pressing Shift F9 here. So you are now in the exception handler. So before continuing, what is a context? Basically, a context contains the current state of the thread. It can be retrieved by a get thread context, but it is also passed to the exception handler via the context record parameter, and then it contains the state of the thread when the exception occurred. So basically, some packers try to use the context record passed in the exception handler, for example, checking the debug registers, and then manipulating the return the EIP when the exception handler returned. So in this example, you are now in the exception handler. So EAX will contain the context record. So it will modify EAX. So EAX plus B0 contains the context record and then the EAX register. So it will try to change the register when the exception handler returned. It will try to change the context of the thread that causes the debug exception. So it will change the EAX to -1 and then increment the EIP, which is EAX plus B8. It contains the context record, the EIP. If you can see here, it will change the EIP. It will increment it by 1. So it means that when the exception handler returns, control will transfer to this address. So you just press Shift F9 again, and then you will be transferred back here. And then EAX will now contain the correct -1 value. So you can do this because the debug exceptions are not automatically passed to the exception handler. You can make it automatically pass to the exception handler by checking this checkbox, int3 breaks and single step breaks. So when you step in int3, it will automatically call the exception handler instead of you just tracing it. So this is the solution. So another debugger detection technique is because several CPU cycles are spent by stepping through to the codes, to the instructions, and the force thinking. So what will happen is that several CPU cycles are spent at that point. So packers check the time spent between instructions, and then if a specific threshold had occurred, the process is probably being debugged. So most of the time, packer try to use the RDTSC instruction or the get tick count instruction. So an example check is like this. RDTSC instruction is invoked, saving the timestamp counter in 2 registers, and then some more instructions there. And then it will call again the RDTSC instruction, and then try to check if the delta is more than 200. So one way to avoid that particular check is to avoid stepping through an important code containing these timing checks. Or if getSeek count is used, you can set a breakpoint in getSeek count. So OLE Advanced has another option against the RDTSC check. What it does is it installs a kernel driver that will set the timestamp disable bit in the control register 4. And if that particular bit is set, once you call RDTSC in a privilege level other than 0, a general protection exception will be triggered. So what it does is it also tries to hook the interrupt descriptor table so that the general fault is handled. What it does is if the general port fault is because of an RDTSC instruction, it will just increment the previously returned timestamp to 1. So this is a demo. So it will first get the timestamp counter using RDTSC, and then return EDX and then EAX. And if you trace, you will see that the delta is higher, making it detect that the reverser is like trying to trace the code. So if you use the RDTSC instruction and then try to use the OLE Advanced plugin. So OLE Advanced plugin has several anti-debug options that you can use so that packers detecting the debugger and other anti-debugging tricks it can patch. So one of those is anti-RDTSC. So you just click enable. So on the first RDTSC instruction, you will see that. So what it does is it had installed a kernel driver that will allow RDTSC to trigger a general fault and then just return a value, just return an incremental value every time RDTSC is called. So once it called the RDTSC instruction again, you will see that the timestamp counter is just incremented to 1 here, so that it will not be detected. So another debugger detection technique used by packers is via the SE debug privilege. So by default, the SE debug privilege is disabled in a process access token. So OLEDBG and WinDBG tries to enable the SE debug privilege in their access token. So what will happen is that the debug process will inherit this access token, and including the SE debug privilege. So packers indirectly check if the SE debug privilege is enabled by trying to open the CSRSS.exe process, because CSRSS.exe is only accessible to system. So if the SE debug privilege overrides the security descriptor, a debug process can open that particular process. So an example check is like this. So in this example, it called the CSR get process ID to obtain the process ID of CSRSS, and then try to open it. If this code was successful in opening it, so the process is probably being debugged. What you can do is set a breakpoint or patch anti-open process so that if the past PID is equal to that of CSRSS, you can just set the return value to a status access denied. So another debugger detection technique involves checking if the parent process is not explored.exe. So if you load the sample in OLEDBG or WinDBG, so the parent process will be different other than explorer.exe. So this can be easily implemented by enumerating all processes and then finding the PID of Explorer, and then comparing it to the parent process. And then if the parent process is not the PID of the explorer.exe, then it probably means that the sample is probably being debugged. So the solution is that you can patch process 32 next W so that process 32 next will fail. So packers will eventually fail in their process enumeration and probably will skip this particular check. So this one I haven't seen a lot in packers and just discussed in anti-reversing forums. So this one involves checking if a debugging session is active by checking the number of objects of type debug object if it's not 0. So a debug object is a kernel object created for every debugging session. It can be queried by NT-query object information class equals to object alt-f information. Basically, this API will return this specific structure. It contains the number of object types in the system, and then tries to object type information contain about all the object types and how many type of objects of that particular type is existent in the system. So basically, what packers can do is call this API and then iterate through the object type information which is listed there. So it will just iterate through the object type information and then compare the debug object string against the type name. And then if the number of handle or the number of objects is not equal to 0, it means that the debugging session is active. So the solution can be you can just patch the returned number of object types to 0 to prevent packers from iterating through the data structure, or all in advance just destroy all the return buffer so that the packer cannot iterate through the data structure being returned. So this one is another classic technique of detecting the debugger. Packers identify debugger via the windows they create. So debugger windows has predefined class names. So, for example, for AllEBG, it has the class name AllEDBG, and that for WinDBG. So this is easy to implement. You just call find WindowX against the window class name, and if the class name and if you find a particular window with that class name, so probably a debugger is running in the system. So what you can do is you can set a breakpoint in find window, and you can manipulate the class name so that it is not equal to AllEBG or WinDBG frame class, or you can just set the return value to 0. So another debugger detection technique is similar to the to debugger windows check. So this one just involves enumerating through the process list, and then try to compare if the process exe file is equal to AllEDBG or WinDBG. So because the reverser may rename the debugger, some packers try to read the process memory instead, so that even though if you rename the debugger, it will still detect it by reading the process memory. So the solution is similar to the solution previously discussed. You can just patch the process 32 next to always fail, so that the process enumeration will fail. I have seen an AllEDBG plugin that tried to install a rootkit so that when the packer tries to enumerate the processes, it will not find AllEDBG. So this one is another classic technique. It involves trying to access the kernel, access the kernel device drivers. It just involves invoking create file against the device name, So in this example, trying to detect soft ice. So this technique is also used for detecting registry monitors, like Falmer Regmon. So basically, you can just set a breakpoint in create file W, and then manipulate the return handle to invalid handle. So this debugger detection technique is specific to OLEDBG. So OLEDBG has an on-access memory, on-access write memory breakpoint, which is separate from hardware breakpoints. This feature is implemented via guard pages. So guard pages provide a way for applications to be notified if a memory access write occurred in specific pages. So guard pages are set via the page guard page protection modifier. So if a guard page is being accessed, so it will throw on status page guard page violation. So, but if the process is being debugged in OLEDBG, the guard pages OLEDBG will just treat it as a memory breakpoint and will not, and an exception handler, and the exception status guard page violation will not be passed to the exception handler. So this is an example code. In this example, it allocated a memory and then try to store a return instruction in it. And then after, it will try to set the page guard attribute of the page. And then it will try to execute the code in the allocated memory. So if the process is being debugged in OLEDBG, no exception will occur, and it will just treat it as a memory breakpoint. So here's a demo. So it will allocate a memory here, and then tries to store a return instruction, and then try to set the page guard attribute, and then try to execute the code at the allocated memory. So if you run it, no exception will be thrown. What will happen is that it will be just treated as a break on access memory breakpoint. So what will happen is that the exception handler will not be called, and the flags will not be set. So it will just detect that the process is being debugged by OLEDBG. So what you can do when this happens is that you can force an exception. So in this example, you can just put an entry, and then return, and then set a breakpoint on the return instruction, and then press Shift F9 for the exception handler to be called. So you see that the exception handler is called, and the AX register had been modified to -1, and then you can just continue. You can just continue tracing, and then the OLEDBG will not be detected. So the next topic is about breakpoint and patching detection. So the first part involves software breakpoints. So software breakpoints are set by replacing instruction at target address by an entry. Packers try to identify software breakpoints by searching for CC, so for the CC in the unpacking stub or the API code. So some packers, instead of comparing if the byte is CC, they will perform a computation in it and then try to compare it with a specific value, so that the check is not obvious. So if packers are trying to detect software breakpoints, so clearly you can use hardware breakpoints, or you can set a breakpoint on the Unicode versions of the API, because some packers are lazy. They will just check the ANSI version, and then, or you can also try setting a breakpoint on on the native API instead. So hardware breakpoints are set by setting the debug registers. So because debug registers are not accessible in ring tree, as most packers try to identify them via the context record passed to the exception handler. So in this example, it will try to throw an exception so that when the exception handler is called, it will get the context record and then try to check the debug registers in the context record if they are not 0. So if that is the case, so a hardware breakpoint is found, and then try to signal the process that it is being debugged by setting the EAX register. Some packers, what they will do is, if they found a hardware breakpoint, they will just terminate or corrupt some instructions. Some packers also try to use debug registers as a decryption key. So, for example, when it is decrypting, it requires that the debug registers are 0. So when you try to set a hardware breakpoint and it uses that hardware breakpoint as a key for decryption, what will happen is that the instructions will be corrupted because the debug registers are not set to 0 or what it expects to be. So patching detection, it involves checking if a patch has been made to the unpacking stub. It just involves performing a checksum. So some use simple checksums, while others use intricate checksums and hash algorithms. So you can try to avoid setting software breakpoints, or you can just use the on-access memory breakpoint by OllyDbg. So this next part is about anti-analysis. So anti-analysis is a way of packers to bore the reverser. This anti-analysis techniques, for example, a packer without anti-analysis, you can, for example, analyze for 30 minutes. But if it have anti-analysis techniques on them, like garbage code, etc., it will take a long time to analyze the code. So the first part of anti-analysis is encryption. Packers usually encrypt both the unpacking stub, the one that unpack, and then also the protected executable. Some packers just use simple XOR loops. And decryption loops are easy to recognize. They're just fetch, compute, and then store operations. So on polymorphic packers, the encryption algorithm changes and also the unpacking stub. So it's an example of a polymorphic packer. So it just fetch a byte and then try to perform computation in it, and then try to store it, and then tries to loop. So compression, so it just reduces the size of the executable. So it has a simple obfuscation side effect because the code is compressed and some data is also compressed. So garbage code. This is an effective way to slow down a reverser. So they try to hide the real purpose of the codes, and then it adds effectiveness to other anti-reversing techniques by hiding them. So it's an example. So in this particular example, this is a decryption routine. When intertwined with garbage code, so this is the equivalent. So we'll see that. So that you will see via looking at the instructions, there's a lot of garbage instructions so that it hides the real purpose of the code. So code permutation. So another technique for anti-analysis is code permutations. It involves, it is used by more advanced packers because it requires understanding of the code and tries to generate equivalent instructions. So an example, instead of using move, it tries to use push and then pop, and then tries to use OR instead of test. So just to show how permutation and garbage instructions are effective in this in the left side, it is a very simple debugger detection technique. But when you use a code permutation and garbage code, that is what it look like. So on the left side, you can analyze it for like you will understand what it does for like 5 seconds. But if you try to understand the one on the right, it will take you several seconds to minutes. So what I do if the packer tries to use a garbage code, I first try to understand if what I'm tracing is really worth tracing. So what I do is I do some what I call trace markers. I can run the packer inside an API logger, and then I will load the packer in a debugger, and then try to set up breakpoints in the APIs being used. So if something went wrong, for example, I will set a breakpoint on virtual alloc, and then set a breakpoint on load library. So when virtual alloc, I had successfully traced virtual alloc, but when I tried to run it and then it failed on load library, then something went wrong between the call to virtual alloc and then load library. So that is the time when I will try to trace it, manually trace it. So another technique I use is I use OllyDbg inside of VMware. So if I'm tracing a very difficult packer, I will try to save the trace state from time to time. So if something went wrong, I can go back to a specific trace state. So anti-disassembly is a method to obfuscate the disassembly produced by disassemblers. So one method involves inserting a garbage code and then adding a conditional branch to the garbage byte. And then the condition for this conditional branch will always be false. So this is an example. So this is a debugger detection technique. So there is some anti-disassembly sequence here. So it tries to push the address of the real instruction here, and then try to have a conditional branch in which the condition is always false, so that debuggers or disassemblers will follow this jump fake address. So what will happen is in this particular example, when you load that in WinDBG, you will see that the disassembly is different from what you expect. So that is the output in WinDBG, and the other is the output in OllyDbg. So this is the disassembly output in AdaPro. So in this particular case, so for packages that use it, so you need to manually fix the disassembly, so which is time consuming. So these are the debugger attacks. So packers employ several techniques so that tracing is not linear. One common way for packers is they try to throw several exceptions. So in this example, it will misdirect execution by exception. So if you're a reverser trying to trace this, and then you just press F7, you will single step on it. What will happen is that you will enter an endless loop. So here, you are tracing the code right now. So if you just press Shift F7, so you'll be baffled by how will the loop finish? So how will I get out of here? So what happened is that it will try to execute the rotate instruction. If you try stepping through it slowly, you'll find that several steps later, you will see that the overflow flag will be set here. So you will see that it is being set, and when the into instruction is executed, it will it will call the exception handler. So what you will do is try to look at the SEH chain, and then look at what the exception handler, and then set a breakpoint in it. And then when the into instruction in0 instruction occurred, it will generate an integer overflow, and then you will need to press Shift F9 so that the exception will be passed to the exception handler here. So you are now in the exception handler. So what this will do now is just try to increment the EAP upon return. So it will increment the EAP by 2. So the next instruction will be this instruction. So you just press Shift F9 to get out of the exception handler, and then you will be here. So you just get past the endless loop when you're tracing it. So here. So this is another debugger attack. What will happen is that some package tries to use a block input when the unpacking stub is executing. So what will happen is that if you call block input, the mouse and keyboard events will be blocked. So what package do is in its unpacking code, it will call first block input, and when the unpacking code finishes, it will call unblock input. So just to show you what happens. So in this example, so this particular sample calls block input, and then we'll call load library. So when I try to set a breakpoint in load library, and then run it, you'll see that I cannot control the debugger. So the mouse here is just working because this is inside of VMware. But if you use the keyboard and it tries to click buttons in the debugger, so nothing happens. So it will baffle you what happened. So if you do not identify the block input API had been called, so you will be baffled on what just happened. So luckily the solution is very simple. You just press Control-Delete, and then you will regain Then you will regain control of the debugger. So also you can just patch black input, so it will just perform a return. So this particular debugger tag tries to hide debugging events from reaching the debugger. Basically, the E-thread kernel structure has a field called hide thread from debugger. If that particular field is set, what will happen is that the debugging events will not be sent to the debugger. So if you try to So in this example, it will call NT-set information to set the set hide from debugger flag, and then let's try setting a breakpoint here. So if you try to execute it, so it had been executed, but what will happen is that what you will see in the debugger, no debugging events will be sent to the debugger, and this is the result in OLEDBG. So you see that what just said happened. So the solution is just to set a breakpoint on NT-set information thread and prevent the call from reaching the kernel. You can set the EAP when you are in the NT-set information thread. So disabling breakpoints. Some packers also try to disable breakpoints. So some packers they try to disable hardware breakpoints by setting the context registers. So they do it by the context registers. So software breakpoints can be disabled by identifying all the interrupt trees, and they can try to put a random byte in it so that the instruction is corrupted. So this is the example. So it tries to throw an exception and then try to set the debug registers to 0, so that all your hardware breakpoints are cleared. So this particular sample uses the unhandled exception filter mechanism. So if an exception reaches the unhandled, if the exception reaches the unhandled exception filter, meaning you didn't set an exception handler in it, the unhandled exception filter will not call the top level exception filter. So what will happen is that if your process is being debugged, the top level exception handler filter you set using the set unhandled exception filter API will not be called. So if you're being debugged, the top level exception filter will not be called. But if you are being debugged, what will happen is that it will just throw the exception to the process as a second chance exception. So instead of setting the unhandled exception filter manually, they will some packers try to set the top level exception filter manually by setting this variable. So this is an example. So if the process is being debugged, what will happen is that the exception will be just thrown to the process as a second chance exception and will stop here. But if the process is not being debugged, the exception filter will be called, and then the execution will continue. So this one is a classic attack against OLEDBG. It just tries to exploit a bug in OLEDBG by passing an improper string parameter to output debug string. So the solution is you can just patch output debug string to perform a return. So this is advanced in other techniques. So some packers have the feature called the process injection. So it's a one method to bypass a firewall. So it involves selecting a host process and then tries to inject code in the host process. So in this example, Notepad tries to inject code into iExplore. So another technique is called the debugger blocker. This is introduced by Armadillo. So it prevents a debugger from attaching to a protected process. So it involves spawning a child process which will contain the unpacked executable. But when you try to attach a debugger to the spawned process, the debugger will just say that you cannot attach the debugger. So as an example, so let's try attaching. Here, this is the child process that we are trying to attach to. So it will say that you cannot attach to the said process. So one way to solve this, which is discussed in reversing forums, is first try to attach to the debugger process. So which is this one. So you can attach to it. And then set a breakpoint on wait for debug event. And then press run it. And then eventually the debugger process will stop on that breakpoint. And then you just trace until user code. And then you are now in the debugger's process main loop. So what you can do next is to run another instance of Oli, and then try to look at the PID. So we will try to attach to this process. So we will try to attach in this process. So what we can do is to, in the debug process, you can push you will try to call a debug active process stop, in which the PID is the PID of the child process. And then you call So once that API is executed, you can now try to attach to it here. So you are now able to attach a debugger in the child process. So another technique used by Packer is called the TLS callbacks. It is a way for a code to execute before the actual entry point. So TLS callback can be easily identified by parsing tools. So address of TLS callbacks contains the TLS callbacks that will be executed before the actual entry point. So you will just need to take note of the TLS callbacks, and then you can set only DBG to stop at a system breakpoint, so that the actual entry point will not be, so that it will stop on that particular NTDLL function. And at that point, the TLS callbacks are still not called. So you can set a breakpoint on the TLS callbacks and then try to trace them. So this is another technique called the stolen bytes. So basically, it involves overriding parts of the code, and then executing it in a specific address instead of so what they will do is allocate a memory and then store the original instructions there, and then overwrite the instructions in the unpacked code with garbage code. So this prevents complete reconstruction by process dumping. So another technique is API redirection. So it makes import table rebuilding difficult. So in this example, a jump to a copy file will be modified to a call to an allocated memory. So on that allocated memory, there will be a copy of the copy file 8 code. So this part has been copied by the Packer, and then also the code pointed to by these call instructions will be executed here, and then but at the end it will transfer execution to this part of the code here. So another technique is via multi-threading. One example is pcrypt. It decrypts the encrypted code in a separate thread, so it makes it is difficult to trace them. So finally, the latest technique used by commercial packers is via virtual machines, because eventually protected codes need to be decrypted, and that anti-reversing tricks will be bypassed. So modern packers try to solve this by transforming the protected code into P codes, and then try to execute them in a virtual machine, so that you will not have the original x86 instructions in the file. So if you are tracing, what will happen is that if you load a sample protected by virtual Packers supporting virtual machines, if you dump the file from memory, what you will see is just the disassembly of the virtual machine and not the original instructions. So you will need some tools to properly parse the P codes so that it will return usable information. So this makes reversing more time consuming, because you will need to parse the P code instruction and how it is translated. So an example is an example of defeating a virtual machines by creating a disassembler can be found at that link. So you can think of virtual machines as visual basic P code compiled samples. So if you load in OLEDBG, so you will not see x86 disassembly. So the tools I had discussed is OLEDBG, and then OLEScript, which you can use. If the packer is difficult, you can try to use it for automatically setting breakpoints and then patching. So OLE Advanced has you can armor OLEDBG against debugger detection techniques and much more. And finally, OLEDump is another tool that you can use for process dumping and import table rebuilding. And also you can use Imprec as a standalone tool for process dumping, and it has an excellent import table rebuilding capability. So just a final demo of how to use these tools. I usually just run the sample. So this is the sample running in memory. So everything is decrypted, and then you can use you will not need to trace this particular pack sample because it doesn't do API redirection, which you need not to disable. So this one can easily be dumped by a process dumping. So Imprec, you just select the process, and then right-click and here, and then try advanced commands and get API calls. It will read all the API calls for process rebuilding. And then right-click again, and then select code sections, and then do a full dump. And then the next thing you will do is try to do a fixed dump. So you will be having the result will be an unpacked code with the import table rebuilded. So you will see that API calls are now that the API calls are properly the import table is properly rebuilded so that you can see the API calls there. So the next tool, if I try Imprec and if didn't properly perform a import table dump, I also try using OLEDBG, and then try to attach to the process. And then use OLEDump. You just dump process. And then you just temporarily set the enter point to like 1000, and then do a dump, so it will automatically rebuild the import table. Then you can just load it in Ada Pro. So any questions? Yes, sir. Excuse me? Mm-hmm. There had been some discussions in reversing forums that you can, for example, there are some packets that if you try to dump them, some parts of the the code is still not decrypted. Some reversing forums said that you can try to use create a plugin that will try to execute the instructions so that tries to execute specific instructions so that they will be decrypted, and then tries to dump it one by one. So. Probably you cannot rebuild it properly. That is the case. So any questions? All right, thank you.